So what we're looking at is an RC circuit, which is a type of an electronic circuit that is used in neuroscience to model the passive properties of neuronal membranes. The term RC stands for resistor-capacitor, which are the two main components of the circuit, and I stands for current. There's also a battery. When there is no current flowing through the circuit, which means that the current measured is zero, at that point the voltage measured within the circuit is known as resting voltage. We'll write that as U rest for the following derivations. Now, as some current flows into the circuit, it will split into parts. Some of it will flow through the capacitor and some of it will flow through the resistor. Now let's put this into an equation. So by the law of conservation of energy, the total current should be equal to the sum of the resistive current and the capacitive current that I just showed you on the circuit. Now let's focus on the capacitive side of the circuit first. As you must have studied in your physics or electronic classes, that capacity equals charge over voltage. Let's simplify this by moving the voltage to the other side, which will be U times C equals Q. Now we know that current is the rate of flow of charge over time. So we will write that as d dt Q. Now bear in mind we're talking about the capacitive current here. So we're going to calculate this as C times du dt equals dq dt equals IC. Just to clarify, the rate of change is denoted by d divided by dt. So we can also write IC as C times du dt. Now looking at the resistor side of the circuit. For this, we're going to have to introduce the Ohm's law, which states that voltage equals resistance times current. Now here, we're talking about the resistive current flowing through the resistor. And by voltage, we mean the voltage across the resistor. Now, this is not the total voltage. The total voltage will be the battery voltage plus the voltage that flows through the resistor. Basically, the voltage across the resistor is total voltage minus the battery voltage, which will be U minus U rest. So if UR, voltage across the resistor, equals R times the resistive current, therefore U minus U rest equals R times the resistive current. Now we are going to feed this back into the original equation, which means the total current equals 1 over R into U minus U rest plus C times du dt. Let's simplify this a bit by moving this to the left side and keeping the signs. Let me write it this way: C times du dt minus 1 over R U times U rest plus I of t. We can simplify it further by multiplying both sides by R, the value of the resistor, and we get R times C times du dt equals minus U minus U rest plus R times I of t. This is the final equation. Let's see what it means. Now, U here is voltage and U rest is the battery voltage. Now R times I, what does Ohm's law tell us? Now the left hand side also has units of voltage. Let's balance them on the right hand side. We are going to denote R times C using a unit of time, also known as tau. Tau is the time constant of this differential equation. Now this is the equation we just derived. R is the resistor, C is the capacitor, but R times C is the membrane time constant known as tau. If you remember, we mentioned that V equals U minus U rest. It's total voltage minus resting voltage. Now we take the derivatives of the same and write them as dV dt equals du dt minus the derivative of U rest. But since U rest is a constant parameter, so it disappears. Therefore, dV dt equals du dt. Let's put this back in the equation and you'll see that we have tau dV dt equals minus V plus R times I of t. Now in this V, the battery voltage has disappeared. To summarize, the passive membrane is denoted by a linear differential equation, which describes that the evolution of a voltage, a potential battery voltage, is included, with the definition of this new variable V, which appears on both sides of the equation.